Okay, so, all right. Whoops. As usual, I made the same mistake. Hold on, let me go back here. Okay, I want to get my little pen here so I can highlight. Okay, so in some applications, a problem is described initially using one basis, but then the solution is aided by changing that basis to a new basis, C. So you have script D and script C, two bases. And you already learned how useful different bases can be in regards to when you studied the coordinate systems in section 4.4. Like, for instance, the crystal lattice for titanium. You learn how those where how the bonds are, depending on where the bonds are, the vectors that correspond to the different bonds are very, very useful to use as a basis. And here they present the problem more formally about when you want to go from one basis to another basis. Okay, and to visualize the problem, consider two coordinate systems in figure 1. Okay, so this is figure 1. Two coordinate systems for the same vector space. Okay, what is the vector space, by the way, in figure 1 in both pictures? What vector space are they using here? Okay, what would that vector space be? Can you name it? Well, in figure 1 on the left, you have vectors b1 and b2. Okay, those are your basis vectors. And in figure B on the right, you have basis vectors c1 and c2. Where do the basis vectors live in both pictures? I mean, is it, and I guess, well, let me ask you this. What's the dimension of the space in figure 1 for A and B? What dimensional space are we talking about here? Okay, that's right, Benjamin. Two-dimensional space. Absolutely, absolutely. That's what we're talking about here. Okay, and all right. So the on the left in figure 1, they have a basis b1 and a basis b2. And then, I'm sorry, they have vectors b1 and b2, which form a basis. And you notice in figure 1, they're not giving you any like scale on the axes, so you can like give a coordinate for vector b1. They're doing that on purpose. They don't want you to get wrapped up into like actual Cartesian coordinates, which you might everybody's kind of attracted to those Cartesian coordinates because you've been using them so long. But in fact, what you have in figure 1 on the left is you have a vector x, and you have a vector b1 and a vector b2 that forms a basis for the vector space, for that vector space in figure 1a. And they're saying that in terms of that basis, script B, which is the basis of vectors b1 and b2, they're saying the coordinate vector of x with respect to that basis B is equal to 3, 1. And you see how on figure 1a, if you move three units, 3 b1 units, 3 b1 vectors, and then add the b2 vector to the 3 b1, you see that you arrive at the at the vector x. Is that okay? Okay, Hung's comfortable with that. Is there any question as to why the coordinate vector of the coordinate vector of x with respect to basis script b, I'll call it b, is anybody uncomfortable why 3, 1 are the entries? Please let me know now if you're uncomfortable. All right, well then let's go to the figure 1b, the picture on the right. There you have basis vectors C1 and C2, okay, and the coordinate vector of x with respect to the basis script C is going to be 6 and 4. And you can see in figure B, well, in figure A and figure B, I'm sorry, figure 1, the picture A on the left and the picture B on the right, is the vector x in the same location in both pictures? Okay. Benjamin thinks so. All right. Who else is seeing that in figure 1, pictures A and B, that the vector x is in the same location in the vector space? The dot for the vector x, that blue dot, is in the exact same location for pictures A and B in figure 1. I'd like to see a few more thumbs up to see if you're comfortable with that. Okay, Andres is comfortable, Catherine is comfortable. Good, good, good. All right, well then the coordinate vector of x with respect to basis script C is 6, 4. Because if you move from the origin, if you move 6 C1 vectors, and then from there add 4 C2 vectors, you arrive at the location vector x. Okay, so different coordinate systems clearly in figure 1a and figure 1b, and the grid in figure 1a and figure 1b, the grids correspond to the differing coordinate systems respectively. But of course, what we would like to do is be able to see how, I mean, can we relate coordinate system A to coordinate system B? Can we relate coordinate system, can we relate the coordinate system in the picture A to the coordinate system in picture B? Can we relate the coordinate system in picture B to the coordinate system in picture A? Okay, that's what our goal is here in section 4.7. And my understanding from one of my colleagues who has some extensive engineer training is that this is extremely important. He mentions, for instance, at University of Maryland in one of the courses, this is extremely important. Okay, all right. That being said, let's go to example 1. Okay, and here, all right, we're going to consider two bases B and C, for a vector space V, such that vector B1 is 4 times vector C1 plus 1 times vector C2, and vector B2 is -6 times vector C1 plus 1 times vector C2. Okay, so that's how B1 and B2 are connected. Those vectors are connected to vectors C1 and C2. And we're supposing now that we have this vector x this vector x, that can be expressed as 3 times the vector b1 plus 1 times the vector b2. Okay, and in other words, the coordinate vector of x with respect to basis b is 3, 1. What we want to do is we want to find the coordinate vector of x with respect to the other basis c. So how can we go about doing this? How do we do this? You know, I want you to have an intuitive feel for how we would do this. So in the solution, okay, in the solution here, the coordinate vector of x with respect to basis c is simply 3 times the coordinate vector of 3 times b1 plus b2 with respect to basis c. But remember, coordinate mapping is a linear transformation. It follows the properties for a linear transformation, okay, a coordinate mapping. So we can rewrite this coordinate vector this way. Okay, we can write it as 3 times the coordinate vector of b1 with respect to basis c plus the vector b2 with respect to basis c. Okay, and interestingly enough, you can express the coordinate vector then as this a product of these two matrices. Okay, the product of those two matrices. The first matrix has column vectors, the coordinate vectors of b with respect to c form the column vectors of the first matrix, and then 3 and 1 are the elements of the column vector. And again, you know, your understanding of matrix multiplication helps you a lot in seeing this. Well, all right. So now, what is the coordinate vector of b1 with respect to c? Okay, if we like this here, what's the coordinate vector of b1 with respect to c? Who can give me the numbers? Good, Hung. Good, Haley. 4 and 1. Good. And we know that. Let me take a little bit of this off here. We know that b1 is equal to 4 times c1 plus 1 times c2. So the coordinate vector of b1 with respect to c, basis c, would be 4 and 1. Okay, what would the coordinate vector of b2 with respect to c be? That's right, Hung, -6 and 1. And that's because b2 is equal to -6c1 plus 1 times c2. Okay, so this is, so then if there are no questions, I'll go down a little bit. All right, so we established the coordinate vectors here. b1 with respect to c, the coordinate vector of b1 with respect to c, and the coordinate vector of b2 with respect to c. There are 4, 1, and -6, 1. And so, but again, you can write the coordinate vector of x. You can write the coordinate vector of x with respect to c then by simply constructing, I got a little too much highlight, constructing this matrix here, whose column vectors are the coordinate vectors above. And so this demonstrates then a theorem. This demonstrates, well, and that matrix, 4, -6, 1, and 1, that matrix is the change of coordinates matrix from basis B to basis C, right? You learned that back in section 4.4. Okay, and so now we have this theorem. We have this really cool theorem, Theorem 15, that connects this all together. Again, we're trying to relate one basis to another basis. Well, that means we need to relate the vectors, the coordinate vectors of one basis to the coordinate vectors of another basis. I mean, that's what we're doing here. And so this is the theorem that relates, that does that. And of course, we established, based on the example 1 we just looked at, we established this result here, that the coordinate vector of x with respect to basis C would equal the change of coordinates matrix from B to C times the coordinate vector of x with respect to basis B. But then, if you wanted to find the change of coordinates matrix of going from basis B to basis C, it would consist of these column vectors here, which are all column vectors of the column vectors are, I want to say this the right way. Well, no, yeah, yeah. We basically, yeah, I guess I was thinking, yeah, we showed this whole theorem. I mean, we've motivated this whole theorem why it's true with an example. And that's how I like to generally, when I see theorems, I like to look at examples to help motivate the theorem. Are there any questions on this? All right, well, okay, so all right, so they have a little picture here. Oh man, hold on. I always do this. Let me go up. They have a nice picture here in figure 2 that shows how you take a vector x, and with the vector x using, I mean, you can express that vector x using different coordinates depending on what your coordinate system is. Okay, they have 2 coordinate systems below. And then you relate the coordinate systems, the coordinate vectors in the coordinate systems with respect to that change of basis or change of coordinates matrix from B to C. Okay, it could be called change of basis matrix or change of coordinates matrix, but it's from B to C. Okay, now you might be wondering, well, what's the change of coordinates matrix from basis C to basis B? How would we get that? Well, remember that we can take both sides here. We can take that equation that we had before and multiply it. Well, I want to say this the right way here. Hold on. Okay, so I'm looking here. I'm looking here at the theorem 15 at the 4 there, and if I multiply on the left both sides of that vector equation with the inverse of the change of coordinates matrix from B to C, in other words, the inverse of matrix P, then we're going to get this. We're going to get this down here. Okay, and so now, if you wanted to find the change of coordinates matrix from basis C to basis B, all you need to do is take the inverse of the change of coordinates matrix from basis B to basis C. Okay, so once again, if you want to find the change of coordinates matrix from basis C to basis B, just take the inverse of the change of coordinates matrix from basis B to C. How many think that's absolutely cool? I mean, how many think this result is a really cool result? Yeah, Eleanor likes it. I think it's pretty cool. Hung likes it. Yeah, yeah, yeah. So, okay, let's look at an example here. Okay, let's look at an example, and this example, I'm actually going to bring it up here. Let's work through an example together here, okay? All right, let me give you a moment to copy this example down. Section 4.7. Okay, so, all right, let's take a look here. Now, here we have basis vectors. Well, we have basis vectors B1 and B2, and we have basis vectors C1, well, and C2 here. So clearly different bases. Okay, what would these sets of vectors be a basis for? What space? Oh, well, I guess it's kind of given to you, right? R squared, right? Okay, so we want to find a change of coordinates matrix from basis B to basis C, and we want to find a change of coordinates matrix from basis C to basis B. Okay, and we want to try to do this in an efficient way. So I'm going to show you how we're going to do this. May I move to the next page? Are we ready to go to the next page? Okay, Lewis is good. Okay. So look at what I do here. Now this is going to seem a little strange at first, but you're going to see it's actually very logical. What I do is I set up a matrix, okay, that has as the first two column vectors are C1 and C2, okay. That's because those vectors are for basis C. And then the next two column vectors are vectors B1 and B2, and that's for basis B. And what I'm going to do, I'm going to let you copy this whole part. But I'm going to do row operations on the entire 2x4 matrix. And I'm going to keep doing row operations until I get the left-hand part of the matrix. I get it as an identity. Okay. All right. Now this has nothing to do with like, you know, an inverse or anything. This is just, let me give you a moment to copy this down. And there's some writing here on the right that is, this writing here on the right is important. So let me give you a moment to copy it down, and then we will discuss it. I generally kind of like to discuss things when students have copied things down a little bit. So, all right, I'll give you a few moments here. Okay, so what's going on here? What's going on here? I set up, well, let's remind ourselves what we're trying to do here. We're trying to find the change of coordinates matrix from basis B to basis C. And apparently, when I set up my matrix like this and do the row operations, once I have an identity on the left side, then on the right side, this matrix here with 6, 4, and -5, -3, that's going to be my change of coordinates matrix from basis script B to script C. Okay, well, why is that true? Well, let's remember what we're trying to do here. I mean, this process, okay, think of it like this. Okay, I got it. Think of it like this, okay? I mean, I'm trying to solve two augmented systems simultaneously. This is the first augmented system. Here's the second augmented system. But another way to think about this is, in other words, I mean, I want to solve for x1 and x2 for this vector equation. Okay, I want to find x1 and x2 such that x1 times vector c1 plus x2 times vector c2 equals vector b1. Okay, all right, and if I find those values of x, then that vector b those values of x would form my coordinate vector of B1 with respect to basis C. Similarly, I want to solve for y1 and y2. I want to solve for those variables that are the variables in this vector equation. Y times C1 plus y times C2 equals B2. Those y1 and y2, those values would be then the coordinates, well, those values would form the coordinate vector of vector B2 with respect to basis C. Okay, so anytime you solve on a vector equation, you're solving an augmented matrix. And so what we have up here is we have an augmented matrix whose left side is 1, 3, -4, -5, and whose right side is -9 and 1. That's one of the augmented matrices. The other augmented matrix is, again, has columns C1 and C2 on the left, but then to the right of the equal sign, you have -5, -1. So you're simultaneously finding, I mean, I could have done it separately, you understand? I could have solved two separate systems of equations, and that would be fine. Okay, that would be fine. But there's nothing wrong in this case with setting it up this way, because what's going to happen is on the left-hand side, when you're done with your row operations, you know, I mean, what do we have here? We have x1 equals 6 and x2 equals -5, right? Okay, we have, maybe I'll put that, hold on here. Let me put that in red. We have x1 equals 6 and x2 equals -5. Okay, so those are the numbers that form the coordinate vector of B1 with respect to C. Okay, but then we also have x1 y1 equals 4, okay, and y2 equals -3, and hence you get that other coordinate vector. Okay, does this process make sense? What I'm showing you here, is this, I mean, I understand it could take some time to absorb, but does it at least initially make sense to you? And how then we get our coordinate vectors? See, if you had a, this is you're dealing in R2, two-dimensional space, but what if you're dealing in 10-dimensional space? Well, 10-dimensional space, if you would need to find, if you had two bases in 10-dimensional space, how many coordinate vectors would be in each basis? That's right, you'd have 10 coordinate vectors. That's right, Ben. And so, okay, so if you wanted to find the coordinate vectors of I want to say this right, the coordinate vectors of the vectors in, I'm sorry, hold on now, one moment. Yeah, if you wanted to find the coordinate vectors of your vectors in basis B with respect to basis C, well, you would have 10 coordinate vectors. So you could solve 10 different systems of equations separately, or you could set it up as one huge matrix. And on the left side, once you had a 10 by 10 identity on the left side, on the right side, you'd have your change of coordinate matrix from basis B to C. Okay, so are there any questions on that? Well, we found the change of coordinates matrix right here. We found the change of coordinate matrix from basis B to basis C. How are we going to find the change of coordinate matrix now from basis C to basis B? You notice the arrow helps a lot in the notation. Here you're going from basis B to basis C. Now we want the change of coordinates matrix from basis C to basis B. So how are we going to find that? That's right, Nafani. Excellent. Take the inverse. That's right, Nafani. That's right, home. Take the inverse of this matrix. And so if we go to the next page, we do that. We do that. So we've already established that the change of coordinates vector of x with respect to basis B would equal the inverse of the change of coordinates matrix from basis B to basis C times the coordinate vector of x with respect to basis C. And therefore, the inverse of the change of coordinates matrix from basis B to basis C would then have to be the change of coordinates from basis C to basis B. And so you just take the inverse and you get your answer. I've not seen this application really in statistics, at least the statistics I studied that much. But again, my understanding from somebody who is a little more familiar with certain aspects of, I mean, my area of expertise is mathematical statistics, but I understand in engineering, this is very, very, very important in certain applications. And I can understand that. We've already seen, we don't have to have even an engineering degree to see how important this is. We already saw this when we studied change of coordinates back in section 4.4, the crystal titanium lattice example. I mean, all right, are there any questions on this example? Who's feeling reasonably good, reasonably comfortable with section 4.7? Okay, good. Thank you, Hung. Thank you, Benjamin. All right, well, what I'd like to do, let me stop the recording.